Welcome to the next video in a course in real analysis. This is lesson 6.1, which I use to indicate that it is a sort of add-on video all about exercises and solutions related to the content of lesson 6, which was on the real number axioms and their basic properties. In this video, we will have exercises that relate to the themes of order being maintained by certain exponents, and the existence and basic properties of nth roots of positive real numbers, and the sums and products of rational and irrational numbers. To begin with, we'll just give a walkthrough of the various exercises. I strongly recommend that the viewer, if you are, using this to learn real analysis like in a course, then you should copy these exercises down, solve them yourself, and then only later compare your solutions with mine. But here's the first exercise. And so we take any non-negative, A and B are real numbers, and a natural number, which I'll remind you, I believe the textbook begins the natural numbers with 1. So the smallest value of n here is 1. And for any natural number n, we will show that a less than or equal to b holds if and only if a to the n is less than or equal to b to the n. And by the way, when I say preserve order, this is what I mean, right? So this is exponents preserving order. So the direction of the inequality is kind of preserved after taking natural number exponents. Next, let's look at this exercise where we let y be a real number, which is in particular greater than or equal to 1, and again a natural number. We'll prove a few things. First, show that y is less than or equal to y to the n in this case, and then take this set, which we generally identify with the set we're going to use to construct the nth root of y, and we'll prove that this is non-empty and bounded above. And that will show that the supremum always exists, and if eventually that will be useful in demonstrating the existence of nth roots of real numbers, of positive real numbers. Now, I'll just point out that we are assuming that y is greater than or equal to 1. Of course, nth roots of positive real numbers also exist when y is between 0 and 1, and we're not addressing that in this video. I will say that for certain related theorems, you could attempt to prove them directly, right? You should go ahead and take all the things that we prove when we assume that y is greater than or equal to 1, try to form the corresponding statement when y is between 0 and 1, and try to prove them. I encourage it, even though I'm not going to go through that here. But when you do prove it, there are probably going to be some opportunities where you can take a shortcut and you don't have to prove it from scratch the way that we've proved everything for this case. What you can do instead is observe that when y is taken between 0 and 1, then its reciprocal is strictly bigger than 1, and then the results that we are proving here apply to it. And so if you can use those results on the reciprocal of y, if you could then take that and relate it back to y itself, then you may be able to find really nice, elegant, short proofs for this particular case. So think about that. I encourage you to attempt it. But moving on to the next exercise, we will demonstrate the existence of the square root of 3. And we will also demonstrate the existence of the cube root of 2. A lot of these will go similar to previous things in either lesson 6, where we demonstrated the existence of square root 2, or some of these will, right, like some of problem 3 you can maybe use as guidance to help you think about how to do problem 4 and so on. But in any case, so these should be somewhat familiar and somewhat similar to previous things, but certainly there will also be differences. And especially here, when we're talking about the cube root, then you're gonna want to, get a similar expression to what we looked at before, but there's going to be some obvious differences, and you'll have to manage that. But anyway, moving on to exercise 5, if you take a rational number and an irrational number, their sum will always be irrational. If the rational number is not 0, then their product will be irrational. And we will also show that there are infinitely many examples of two irrational numbers such that their sum is an integer, and they're in another infinite family of examples where the product of two irrational numbers is an integer. Next, we'll demonstrate that root 2 plus root 3 is irrational. And for the final exercise, we're basically going to generalize what we saw in exercises 3 and 4. So this time, rather than specifying 2 or 3 or whatever, we will just take an arbitrary x greater than or equal to 1. We will define its nth root for, I should have specified that n is some natural number, but we are going to define y equals x to the 1 over n. So this is like defining what x to the 1 over n means. It means, by definition, at least for me, the unique non-negative number such that y to the n is equal to x. So that's our definition of this notation, and we will demonstrate that there exists such a number. So we'll have to demonstrate that it exists, it satisfies this equation, and also that it is unique. And then once we have that, if we let a and b be any two real numbers which are at least 1, then the mth root, again for m in the natural numbers, the mth root will be at least 1. The mth root is order preserving, and it has these two familiar exponent laws. And that's the final exercise in the set. So if you're going to solve these on your own, I encourage you to hit pause or stop the video, solve these on your own, and then compare your solutions with mine. So here we start with the first exercise where we let a and b be non-negative real numbers, n a positive integer effectively, and we'll show this if and only if claim, which says that essentially taking the exponent of n preserves the order of the inequality. So we'll do this proof by induction, which I think makes good sense because, after all, we do have a natural number, and perhaps also because, well, how else would we do this? Well, maybe there's another good way, but this is what came to my mind. So in any case, where n is equal to 1, that's the base case. The inequality, or well, rather the if and only if statement, reduces to a trivial correct if and only if statement. So there's not much need to elaborate on that. Okay, so let's now fix any n, which is at least 1. And then we will assume for the inductive hypothesis that this if and only if claim is true for this n. And now we have to prove the if and only if statement for n plus 1. That means we're going to start from the left to right, which is to say the only if direction, and assume that a is less than or equal to b, and then we're going to try to prove that the order is preserved with the n plus 1 exponent. And so we're going to start from a to the n plus 1 and try to arrive through a sequence of less than or equal to's, more or less, at b to the n plus 1. How are we going to do it? Well, as often is the case with induction, we do something to reduce this to the case of n, And with an exponent like this, a good way to do it is pretty obvious. We just split the a to the n and the a. Now, we, by inductive hypothesis, already know that a to the n is less than or equal to b to the n. So we can sort of exchange them and get an inequality. Also, by the assumption for this left to right direction, a is less than or equal to b. So if we exchange those, we get another inequality. And so we arrive at b to the n times b, with the inequality pointing in this direction. So everything seems like it's going exactly correct. And in fact, at that point, I don't know why I said a less than or equal to. That's an equal to, right? That is the same thing as b to the n times b. That's b to the n plus 1, which is exactly where we wanted to arrive. And so the proof is complete here. Next, we're going to proceed in the right to left direction. And so for this, it's not quite so obvious how we deal with the right to left. That would be assuming that a to the n is less than or equal to b to the n, and somehow trying to arrive at a less than or equal to b. But how you make that move is not very clear. What I feel is much clearer is to attempt the contrapositive. So the contrapositive would have us negate the consequent, and that means assuming that b is strictly smaller than a. From this, we would want to work this way and derive the negation of the antecedent. So we are working toward the statement that b to the n is less than strictly a to the n. But in fact, this move, right, going from here to here, is almost exactly the same as what we've already done above. So rather than detail those steps, I'm going to basically leave that to the viewer. It should be, I think, rather straightforward. So we now move on to exercise number 2. And so let's recall what it says. We're going to take a positive real number that is, moreover, at least 1, and a natural number n. And we will show that it satisfies this inequality, y less than or equal to n. That's where we're going to begin. Okay. Again, this is a natural number kind of claim, and therefore it makes sense to proceed by induction. The base case is trivial, as before. And now we're going to, actually, before moving on to the inductive case, I do want to make a note that is going to be useful when we get into the induction. So let's go ahead and remark on this now. Since we are assuming that 1 is less than or equal to y, then if we multiply throughout by y, we get y is less than or equal to y squared. And that is justified by compatibility, because I know I can take this inequality and multiply throughout by y, because, of course, y is positive. And so by compatibility, I can do that. Okay, getting on to the induction. Suppose that n is a number at least 1, and we will assume for that n that the claim holds, that y is less than or equal to y to the n. And now we're going to talk about the case of y to the n plus 1. As always, for induction, we split this apart. I know that y to the n is itself greater than or equal to y, so I can perform that substitution. And we get y times y, which is y squared. Now that, by the note that I just made before moving over to this slide, we know that y squared is greater than or equal to y, and so we have exactly what we needed to show. Now, to move on to the next part, recall the next part was about this set, L, defined in this way. And what we wanted to show is that this set is non-empty and has some upper bound. Now, the fact that it's non-empty, I think, is pretty straightforward. We know that it must contain the number 0, because after all, 0 to any integer or natural number exponent is equal to 0. and then 0 is going to be less than or equal to 0, so that part's really easy. Since we assumed that y is a positive number, in fact, greater than or equal to 1, but all that matters is that it's positive, then we know that 0 is less than y. So 0 satisfies all these conditions and therefore is an element, and of course is greater than or equal to 0. And so since it satisfies all of those conditions, then it's an element of L. So that part's really straightforward. But let's now show that it has an upper bound. And in particular, I'm going to show that y is an upper bound for the set L. So let's take an arbitrary element x out of L. By definition, what we know is that x to the n is less than y. And there's more, but that's all I need right now. And then we also know that from what we proved earlier, y itself is less than or equal to y to the n. So we get that x to the n, right? This all the important part, right? Extracting kind of what I want to focus on here is that we get y to the n is strictly less, sorry, x to the n is strictly less than y to the n. And then we know from a previous result that this is true if and only if. Now, this is a strict inequality. We proved it for an inclusive inequality, but proving it for strict inequalities would be rather straightforward. So I'm going to assume that the viewer can prove that if they need it proved, but I'm going to just help myself to the result and say that since x to the n is less than y to the n, therefore x is less than y. And that demonstrates that y, as I claimed, is an upper bound on the set L. Finally, by the least upper bound property, or the completeness property, the supremum of L must exist. Okay, next exercise, we're going to show that root 3 is a real number, and we're going to proceed almost exactly the way that we did with root 2. So we're going to define a set of all things whose square is less than 3, and non-negative just to keep things simple. We now know, by the way, from the previous exercise, that therefore that set is non-empty and bounded above. I think here I actually elaborated in this particular case about that, but I mean, honestly, we don't even need to talk about that due to the previous result. But anyway, so we know that it's non-empty and bounded above, so the supremum exists. And yeah, and this is more of justification that we no longer need. And in this video, I'm only going to show that alpha squared is less than or equal to 3. And that's because in the other, right, when I was doing the square root of 2, I showed that 2 is less than or equal to alpha squared. And so here I want to just do the other side of that, but I'm still not going to do the proof all the way out, because I think once I show you one side, it should be reasonably doable for you to complete the other side on your own. And so for contradiction, we assume that 3 is strictly less than alpha squared. Now, somewhat similar to how we did things with root 2, but this time going in the other direction, right? So instead of trying to find a bigger number, I'm trying to find a smaller number, but I do still want this smaller number, alpha minus epsilon. I'd like its square to be bigger than 3. And why do I want that? Well, what that would tell me is that therefore alpha minus epsilon would be an upper bound for the set L. But we would also know that so long as epsilon is chosen as a positive number, then alpha minus epsilon would be strictly smaller than alpha. And so, these two together would imply that we have a smaller upper bound on the set than alpha, but that contradicts the notion that alpha is the supremum of L. The supremum is the least upper bound, so there shouldn't be a smaller upper bound. So that's how we're going to derive our contradiction in this situation. So there we have it. So we've set up our goal, very similar to how we did it with root 2. Let's note that this is equivalent to this inequality. Let's, as before, kind of solve for everything other than epsilon. So I'm basically going to move epsilon and epsilon squared to the other side of the inequality. And I'm going to take the 3, move it over here, and this is sort of priming me to find the choice of epsilon, which satisfies this. Now, we can, in a way, sort of shortcut this one in particular, because with negative epsilon squared being necessarily a negative number, then we can just disregard it, right? It doesn't matter what the choice of epsilon is. This, inequality is always going to be satisfied. And therefore, all we really need to focus on is satisfying this inequality. And right, because it will immediately follow, once we have that 2 alpha epsilon minus epsilon squared is immediately going to be less than 2 alpha epsilon. So as long as I can make 2 alpha epsilon less than alpha squared minus 3, then right, everything follows immediately. This is maybe just a little bit of a cheat that won't generalize when we take things further, but at least for now, let's just use the cheat and say that all I really need is I just need this. And that's so easy to satisfy. You just divide by 2 alpha, and we have all we need for that. If we need choose any epsilon that is like this, which is to say smaller than this quantity. Well, how do we get something smaller than this quantity? Easy enough, just take that quantity, divide by 2, because we know it's positive. So if you divide by 2, you'll get another positive number that is smaller. And so, having chosen epsilon in this way, we now know that it is a strictly positive number. Therefore, if we compare it to alpha, at least we know this, right? That alpha minus epsilon is strictly smaller than alpha. But also we know, because of where this all came from, that that we must have that 3 is smaller than alpha minus epsilon squared. You might wonder, and maybe it's actually a good idea to just go ahead and demonstrate. Like, we know, based on the logic of how we constructed alpha minus epsilon, that that's got to work out. But it might be actually nice to do a more concrete demonstration that that is correct. So here I've written a little bit out. So we'll start from alpha minus epsilon squared. Our goal is to demonstrate that with epsilon defined as we have chosen, that this thing must be bigger than the number 3. So we're going to work towards somehow trying to get the number 3 here. Of course, I can just multiply this out, get this expression. In one particular place right here, I can exchange epsilon for its definition. Over here, I'm not even going to bother, because I know I just want to drop that, right? If I just drop epsilon squared, which I know to be a positive quantity, it's easy enough to infer that when I drop that positive quantity, then I get a strictly smaller quantity. From there, where can I go? Well, I do a little bit of algebraic simplification so that we get this. It should be relatively easy for you to work out how I got from one part, right, from the gold to the blue there. But okay, now that we're standing here, you wonder, well, where do I go from here? I'm trying to show that this thing is bigger than 3. I'm trying to get towards the quantity 3. Well, there's no direct avenue that seems obvious, but you think, well, what do I know about alpha squared? Well, the main thing that I know about alpha squared is the assumption that we made earlier, that it is strictly bigger than 3. So maybe what I ought to do is somehow introduce this, like, alpha squared minus 3, right? That's just sort of a quantity that seems to play nicely with what we know about alpha squared. So I minus 3, but then I also plus 3. So if I put those together, right, I've got a minus 3, but I also plus 3. So I put the 3 and the 3 together, I get 6. Okay, cool. Now, the whole design behind sort of making that move was that I know that alpha squared minus 3 is a positive quantity, and therefore, again, with the logic that if I drop this positive quantity, and I'm going to leave it to the viewer to sort of, if you need to think more about the full justification for this move, then feel free to do so, but I'm going to say that if I drop that quantity, that I get a smaller thing because it's positive. And so then this turns into being bigger than 6 over 2. And 6 over 2 nicely simplifies to just 3. And there we have it. There is a sort of more concrete, complete demonstration that my chosen alpha minus epsilon, when you square it, you get a quantity that is bigger than 3. So that now fully justifies what I wrote there. But now getting back to the rest of the proof, so I now claim that with all of this in order, alpha minus epsilon is itself an upper bound of L. And in fact, the proof of this is very much like the proof of the previous problem, one part of it, where if we take anything out of the set, we know by definition that its square is less than 3, but also we just demonstrated that 3 is less than alpha minus epsilon squared. So we get that x squared is less than alpha minus epsilon squared, and this then implies that x is less than alpha minus epsilon. That's the demonstration that alpha minus epsilon is an upper bound of the set L. And here I'm basically just reiterating some of that. But again, the main logic of this argument is that since I now have an upper bound of L, which is smaller than alpha, therefore alpha cannot be the supremum, but it was assumed to be the supremum, so that's a contradiction. So, okay, moving on to the next exercise, we'll now look at a cube root. And so, very similar to all of what we've talked about before, we'll define this set, this time using a cube, and set it less than 2 in this particular case. Alpha is the supremum of that set. For contradiction, I'll only work on this side, so for contradiction, we'll assume that alpha cubed is smaller than 2, but, and this will show that 2 less than or equal to alpha cubed once we reach a contradiction. But, okay, as usual, we are seeking a particular choice of epsilon, which is positive, and since we're on this side of 2, we'd like alpha plus epsilon cubed to be smaller than 2 still. Okay, multiplying out alpha plus epsilon cubed, this time we get this result. And if you're not familiar with it, which I think in a discrete math class, you should be familiar with the binomial theorem. So hopefully that's recognizable, but that's the sort of ideal way to get a sort of quick expression that is nice and simplified when you take, like basically anything that is, well, essentially of this form. So anyway, so that's using the binomial theorem to get this expression nice and quick. We, as usual, move alpha cubed to the other side, leaving our epsilon terms on this side. And now we have 3 conditions to make, with this sort of intuition that we would like each of these 3 terms that are over here to each be less than a third of the target quantity. So slight changes, but I think they're all very reasonable to guess. And so, well, with this one, right? This we know we can just make an obvious choice, or there's an obvious condition on epsilon to make that choice. Here, we will somewhat predictably, based on things we've seen so far, use the fact that we're gonna design epsilon so that it is less than 1, and therefore when we square it, that's just less than epsilon. And so again, right, the idea is that we can simplify this and look only at epsilon to get that less than the target quantity. And once it's like that, right, because we have epsilon less than 1, once it's like that, then all we have to do is divide the 3 alpha to the other side, and we get an easy and obvious choice for epsilon. And again, right, nothing very different. When this is a cube, that will still be less than epsilon. We would then like epsilon to be less than this quantity, and so we simply take epsilon less than that quantity. Now that we have three conditions to satisfy, or four if depending on how you like to count, then we will set epsilon to be any number smaller than the minimum taken over these three target quantities, and also with a 1 there, so that we ensure that whatever epsilon is chosen, it will always be less than 1, and therefore the rest of the logic that we used here will be valid, basically. So we can choose any number smaller than this minimum. If you want to, you could take epsilon to be equal to this minimum, blah, 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 all divided by 2, right? Just anything like that will get you a quantity that is smaller and still positive. So once we have chosen epsilon in that way, then we will basically, because of everything that we've discussed so far, it will become very clear that alpha plus epsilon cubed will again be less than 2. As I showed in the previous problem, you can do an explicit, or at least a more explicit demonstration of this claim, but I'm not going to spend the time to do that right now. In either case, what we now get is, like in the root 2 proof, that alpha plus this positive epsilon is then an element of the set. Because it is an element of the set, but it is also bigger than the value alpha, then this means that alpha cannot be an upper bound of the set. But we know that it is an upper bound because it is the supremum. That's part of the definition. And so we've reached a contradiction. And now we know that 2 is less than or equal to alpha cubed. And again, the reverse direction is left to the viewer. So I call that Halmos, right? The Halmos. Proof complete. Next, we will show that the sum of a rational and an irrational number is an irrational number. So let's start with that. Let's take a rational number. So I'll say P over Q is in the set of rationals. What that means, right, somewhat implicitly. I mean, writing it like that doesn't make it as explicit as it could be, but what I mean when I say that, and I'll just kind of I'll just throw that out without more explanation because it's kind of obvious what I mean, that P and Q will be integers and Q is non-zero, and that's the rational number that we're talking about. We will also take a value R in the set of real numbers but not rational numbers, so that's the set of irrational numbers. I think that's fairly clear. And we will suppose for contradiction that when you sum these two together, you get a rational number. Well, again, what does it mean to be a rational number? It means that you have an integer A, integer B, and B is not 0. And so I'm leaving, I'm talking out some part of the logic here more than I am writing it out, but it's just to be quick and to hopefully be somewhat clear. And so, okay, so from that, what do we get? Well, we can certainly subtract PQ to the other side. We can add fractions in the way that we know that rational numbers work. And this is consequently a rational number. How do I know that it's a rational number? Well, certainly the numerator is made up of nothing but integers. And the denominator, well, we knew that Q was non-zero. We also knew that B was non-zero. Therefore, when you product B times Q, you get a non-zero integer, and that makes this a rational number. So since this is a rational number, but we assumed that R was not rational, therefore, we have a contradiction, and that part of the proof is complete. Okay, next, we'll do it all over again, but with products. So we'll show that so long as P is not 0, right, we need the further assumption that the rational number is not 0. So we assume that P is not 0, and we'll show that the product cannot be a rational number. If it were a rational number, we'll call it C over D this time, then R would have to equal C over D times Q over P. And that must exist because we know P is non-zero. So I can do this because we assume that P is non-zero. We also are assuming that d is non-zero, therefore dp is non-zero. The numerator is an integer, and therefore that makes this a rational number. Yet again, that delivers a contradiction. Next, we're going to show that there are infinitely many irrational numbers which sum to a natural number. And in particular, if you just fix any irrational number and then we let n be any integer, then this is an irrational number. We just showed in the previous exercise that r minus n is also an irrational number because, after all, every natural number is also a rational number. So r minus n is also irrational from what we showed. Well then, when I compute their difference, it simplifies to n, which is an integer, so that shows that the sum of r together with this whole number, thought of as adding the negative version of it. Anyway, that gets you a natural number, so that's infinitely many sums of irrational numbers that result in a natural number. And then, likewise for products, we'll have to assume that r is non-zero, we don't have to assume r is non-zero because we know it's irrational and 0 is rational. So we don't need to assume that r is non-zero. We need to assume that n is non-zero. Because only when n is non-zero do we know that this is an irrational number. You may want to, do a little more work to prove some of what's going on here, but I think it's fairly clear. So the infinite family of products that we're going to consider then is r multiplied with n over r. And so that's an irrational times an irrational, and the result is a natural number. So that shows that there's an infinite collection of pairs of irrational numbers such that their product is a natural number. So proof complete. Okay, next we show that root 2 plus root 3 is irrational. And the proof for this is, kind of what you're used to in a discrete math class. So we're going to assume for contradiction that it's a rational number. And so that means that it's equal to a over b, where a and b are integers, b is not 0. From that assumption, and by what we simply mean by these square roots, is that if we square them, the square of root 2 is 2, the square of root 3 is 3. And then when we sort of simplify everything, we get this expression. Now, I don't think it should be too hard to demonstrate that root 2 times root 3 is the same thing as root 6. So, although there is a bit of a step there that I'm skipping, I don't think it should be too hard to fill in. So let's go ahead and write the middle term, which comes from doing root 2 times root 3. Right, that's the result of multiplying out this root 2 plus root 3 times root 2 plus root 3, right? So if that wasn't clear, right after distributing this, you get this result. And so then from here, we can subtract 5 to the other side, right? Put the 2 and the 3 together, subtract the 5, divide the 2, and we get that root 6 is equal to this thing over here. Well, if you simplify that out using just normal, arithmetic rules on rational numbers, then you can show that this is a rational number, right? It has an integer numerator and a non-zero integer denominator. This is a rational number. But through a fairly standard proof, we know that root 6 is not a rational number, and therefore we get a contradiction, right? So it's both not a rational number and is a rational number, so contradiction, proof complete. And finally, for the last exercise, we're going to let x be a real number, at least 1, and we are going to define the nth root as the unique non-negative number satisfying this equation. And we're going to show initially that this thing always exists. of course, the proof is just a generalization of what we've been showing already. So, as usual, we're going to set L equal to this set of non-negative numbers, which for which the elements when you take their nth power is less than x. So you hear, this is like talking about, if we were talking about the cube root of 2, for instance, right? Then x would be kind of like the number 2, and n would be the number 3 if we were talking about the cube root of 2. Anyway, from what we've shown, I think it was back in exercise 2 of this video, the set must be non-empty and bounded above, so its supremum exists. And we will show, right, what I used to call alpha, I'm now going to call y to the n in this particular case. And we will show that that y to the n is equal to x. And that will demonstrate the existence of a number satisfying this equation. As usual, assume for contradiction that y to the n is smaller than x. And at some later point, we should assume that y to the n is greater than x. Right? We get a contradiction in both cases. Okay. In this case, as usual, we seek a positive epsilon such that y plus epsilon to the n is still smaller than x. And without explaining that much more, because we've been through it a few times, then let's jump into this expression, which we can simplify immediately by the binomial theorem, which is kind of what we have already seen before. So there's the binomial theorem. We know that what we standardly do when we expand with the binomial theorem is that we split off the, what used to be alpha squared or alpha cubed or whatever. In this case, that's y to the n. So that's the case where we set the index k equal to n. So you get n choose n, that's equal to 1. You get y to the n, and you get epsilon to the 0. So when we split off that nth term, all that results is y to the n. And so this is what we're looking for. As we have done in each of those other cases, we move y to the n to the other side so that we are, in a better position to sort of solve for epsilon, so to speak. Our strategy is to take this quantity and divide into n equal pieces and make each term smaller than 1/nth of the target quantity. So that means that if this is an arbitrary kth term of the binomial, then we want it smaller than 1/nth of the target quantity. Okay. We will, as usual, choose epsilon smaller than 1 so that we know no matter what positive exponent of epsilon we take, that we always get a smaller quantity. And so as long as we ensure that, and we will, then what we want is just to satisfy this inequality. And for this, we can merely take everything other than epsilon and divide it to the other side. Now, this produces a sort of indexed family of quantities. And so we form the set of all of those quantities. We put 1 together with that set, take its minimum, divide by 2, and that is our choice of epsilon. We can now give an explicit demonstration that this y plus epsilon, when raised to the nth power, is strictly less than x. And so how do we do that? Well, we've kind of seen it before. We expand by the binomial expansion. We split off the nth term. We take each one of these epsilons and use what we know, which is to say that replacing it with just epsilon gets us a greater quantity. And then if we take that epsilon and in turn replace it with what it is equal to and clean up some of the algebra, so sort of long story short, this is what happens after substitution and some algebra. Here, since we are summing n terms where the index k does not occur so that it is effectively constant with respect to the index k, then we simply multiply by n. And so after multiplying by n, the n's cancel, and it reduces to just x minus y to the n. The y to the n's cancel, you get just x, and that demonstrates the desired result. As usual, because we have now finally demonstrated all of those claims, we have an element of the set L which is bigger than y. Y was supposed to be the least upper bound, but it's not even an upper bound. So there's our contradiction. So there we have it. We now know that, in a sense, nth roots exist, although we do need to prove uniqueness. So how do we show uniqueness? Well, suppose that any number, we'll call it z, also has the property that z to the n is equal to x, and z is a non-negative number. And now we want to prove that y and z are equal. Okay, well, as may be somewhat predictable, given the themes of our proofs here, we will assume for contradiction that z is smaller than y. Well, if z is smaller than y, we know that z to the n is smaller than y to the n. That's something we have from an earlier result. Well, z to the n was assumed to be the same as x. Y to the n is assumed to be the same as x. Then we have that x is less than x, which is a contradiction, so this cannot be true. We could do the reverse in the same way. The upshot is that y is equal to z, and that demonstrates uniqueness. Now that we have demonstrated the existence of nth roots, then we can move on to these other parts of the exercise. So for instance, we want to show that if A is itself at least 1, and so all the earlier theorems that we've demonstrated about real numbers at least 1, they apply here. And so we're going to use this if and only if that we've used before, but this time we're going to kind of use it in reverse, so to speak, right? Or at least the reverse of what we've done before. So anyway, so what we know is that this inequality holds if and only if raising each part of it to the nth power holds in the same direction. I mean, that was an if and only if that we proved about this, and m is a positive integer exponent. And so we're free to, right? Like, we know that these two things hold if and only if. Well, after all, 1 to the m is equal to 1. That's very easy to prove. And a to the 1 over m to the m, well, just by definition, and we know that these things exist, then we know that this is the same as just a. So we have that 1 is less than or equal to a, which we assumed, right? That this must be true because it was our assumption. So therefore, by the if and only if statement, our desired statement must also be true, that 1 is less than or equal to a to the 1 over m. Okay, so there's the demonstration for part 1. Let's move on to part 2, and it's going to be very similar. We know that this inequality is true if and only if what you get when you raise both sides to the nth power is true. But since what you get when you raise both sides to the nth power is a less than or equal to b, and that was our assumption, then the proof is complete. For part 3, we'll assume that these two numbers have the same base, and keep in mind, right? So basically, what we're going to show is that this quantity, right? This quantity, a to the 1 over m, b to the 1 over m, has the property that defines ab to the 1 over m, right? If we show that quantity has the property which defines this quantity, then they must be equal by the uniqueness result of earlier in this part of the exercises. Right, so that follows from uniqueness. But then what is the property that defines ab to the 1 over m? Well, it is the property that if you take its nth power, you get ab. That's the defining property. So that's what we're going to show. Okay, so let's take this nth power. Well, we know that since m is an integer and these are two real numbers, then we know by properties of integer exponents that it distributes, right? That we can distribute the mth power because m is a positive integer. Now, here, one by one, right, that turns into a, this turns into b, and we're done. And for the final part, we approach this very similarly. We are taking this quantity, and we are showing that it satisfies the property that defines a to the 1 over mn. Namely, we're going to show that it has the property that when you raise it to the mn power, you get a. That's the defining property, and so equality will follow by uniqueness if we show that when you take the mn power, you get a. Okay. Well, again, by integer exponent properties, we know that we can split up the integer into a power of a power, so to speak. And then the 1 over n and the n from what we know about nth roots, right? The definition of nth roots, that the 1 over n and the n, when they are stacked on top of each other like that, by definition, they cancel, and you're just left with a to the 1 over m. Again, by definition of mth roots, that then turns into a, and that is exactly what we needed to show, so the proof is complete. And I'd like to end on an invitation to ask questions, so if you found anything confusing in these videos, please leave a as clear and specific a question as you can in the comments. If I can address it in the comments, I will, and if it takes more than that, I may make a video and include it in the playlist.